Welcome to the first lesson of Microprocessor Basic Computing Concepts. I'm Dr. Abdul Rahman Qawasmi, College of Engineering, Majma'a University. Some history. The first microprocessor or computer is invented by a German scientist named Konrad Zuse, who worked as an engineer for Henschel Aircraft Company in Berlin. This computer was made from electromechanical components and it had a very low processing speed around 5.33 Hz, which, as you know, very slow speed comparing to the latest multiple gigahertz microprocessors. In the heart of the computer, there is our microprocessor, which is a tiny square silver of silicon that's etched with a microscopic network of gates and channels through which electricity flows. This microprocessor we call Central Processing Unit or simply CPU. These gates or transistors are connected by channels, wires, or lines. In order to be familiar with the basic components of the microprocessor, let's see the calculator model of computing. In order to calculate at least one simple arithmetic operation, such as 2 plus 3, we need three main steps or main three components. First, we need the instruction, and the instruction means add or subtract or multiply or divide the data that we will use to perform this arithmetic operation, and of course we need to store the result. So the code stream contains two types of operations: arithmetic operations, that is a part of the data stream, and also we have what we call code stream, which contains opcodes or operators. You cannot work with one of them separately, so you need instructions and data in parallel way to perform your arithmetic operations, for example, as a simple operation that can be used simply using a calculator. So the kind of simple calculation described above represent the sort of thing that we intuitively think computers do, like a pocket calculator. The computer takes numbers and arithmetic operators such as plus, minus, etc. as input, performs the requested operation, and then display the results. So instruction, data, and results. The five-layer model of computing. Of course, inside the computer, there are a lot of or a huge amount of numbers that they are shuffling from one place to another place. We are reading and we are writing these numbers, we are erasing these numbers, writing different numbers in different locations according to a set of inputs, a fixed set of rules for processing those inputs, and the prior history of all the input that the computer has seen since it was last processed until predefined set of criteria are met that cause the computer to halt. So these numbers that are moving from one place to another place, they are moved within the instructions and to have finally the result based on the program that is programmed by the user. The stored program computer. Let's see. If you want to use data or instructions to execute or to perform an arithmetic operation, of course you need to read this data or to write this data from that we call storage area. So the storage area is very important to read and write the numbers that we need in order to perform our arithmetic or logic operations. Also, beside the storage area, we need that we call arithmetic logic unit. In this unit, it is a part, of course, of computer, and it can perform arithmetic operations such as addition, subtraction, and so on numbers from the storage area. And in this case, you see that there is a direct relationship between the ALU and the storage area for reading the data and storing the result. In order to make this connection between the ALU and the storage area, we need what we call bus. This bus is needed to move numbers between the ALU and storage. It is some means of transmitting numbers is required. So the ALU reads and writes data from the storage area by sending and receiving the data using buses. We have two types of buses. Buses, they are required for moving the data, and buses, they are required for addressing of data, and we will talk about this in the future. Now, as you see, this is our stored program computer. We have storage area, we have ALU, and we have buses. As you see, the black line represents the flow of instructions, and the white represents the flow of data, and the gray line represents the results to be stored back in the storage area. So the modern computers ability to store and reuse pre-recorded sequences of commands makes it fundamentally different from the simple calculating machines that preceded it. Prior to the invention of the first stored program computer one, all computing devices from the abacus to the earliest electronic computing machines had to be manipulated by an operator or group of operators who manually entered a particular sequence of commands each time they wanted to make a particular calculation. So in this case, we have computer, we have to write our program. Our program contains, of course, from instructions and data. After finishing our program, we are running this program from the first line until the final line to have our final result. The register file. As you know, and we said before, there is a direct connection between the ALU and the storage area. And the storage area has a big size, and to look for specific data in the RAM, it will need time, and if we want to use several numbers for reading and storing. We have to work. We have to access the RAM several times, and it will take more time than needed. So, in order to make the processing speed more effective, and if we use numbers more than one time for our calculation, it is better to use what we call the register. The register can be defined as a small storage area that can be accessed for reading and storing very fast. And these registers, they are of different purposes that we can use between the ALU and the storage area. So the registers used to store small amount of data that can be used frequently by the microprocessor, and there will not be necessary to access the RAM frequently. The register file, as we said, it connect. It is connected directly to the ALU and to the RAM at the same time. To execute an add instruction, for example, the ALU must perform the following steps. First, to obtain the two numbers to be added, you need two numbers from two source registers. In this case, we are assuming that we have two registers, and in these two registers, our two numbers that we will use for adding, they are stored there. Secondly, we will use the ALU to add these two numbers, and of course the result of addition will be placed back in that what we call destination registers. In this case, we used three registers, two registers as source of data, and we called source registers, and one registers for storing the result, and we call a destination registers. This, of course, this program is correct if we assume that in the source registers our numbers, they are ready for using by the ALU. But if our numbers, they are stored in data and they are not ready in the source registers, we have to add two extra steps. First step, to load first number from the main memory to one of the source registers. Secondly, we have to load the second number from the main memory to the second source registers. After that, we can make the addition operation and the store operation of the result to destination registers. So upon receiving an instruction commanding it to perform this addition operation, the ALU is our simple computer would carry out the following three familiar steps. Read the contents of registers A and B as source registers, add the contents of A and B using the ALU, and write results to register C, which is in our case here the destination register. We said or talked about storage area, main memory. This memory or main memory we call RAM. RAM means random access memory. We use this memory to store the data. We mean by data mean instructions, and the data for the data stream and the instruction stream and their addresses. So this data is stored in the main memory, and it can be used directly by ALU, or we can use it through registers. We have here an example that contains all the necessary steps to understand how we can use the RAM and ALU to perform an arithmetic operations such as addition using, of course, registers. So to add two numbers stored in main memory RAM, the computer must perform the following steps. First of all, I said to load the two operands data, the two numbers that we need from main memory, into the two source registers. Secondly, we add the contents of the source registers and place the results in the destination registers using, of course, the arithmetic logic unit ALU. To do so, the ALU must perform these steps. First, the ALU will read the contents of source registers A and B. Then it will add the contents of these registers A and B. After that, the ALU will write the result to the destination register C using the output. So the ALU has two inputs and one output. Two inputs for instructions and data, and one output for the result. After that, if it is the final result, you will move the result from the register C again back to the main memory or RAM. So in this case, you took your main numbers from the memory, you added them and stored the result again to the main memory, but you used the registers as sources and destinations, and the registers, they are connected to the ALU. A closer look at the code stream, the program. The code stream is very important because it contains instructions that the ALU needs to perform our arithmetic and logic operations. So using these instructions, the ALU will perform all our needed operations line by line or instruction by instructions. General instruction types. We have two main types of instructions. The first type is arithmetic instructions. In this case, these instructions tell the ALU to perform an arithmetic calculations. For example, add, submultiplication, and division. Secondly, we have memory access instructions. These instructions we are used to access the RAM or the main memory for loading and storing. So the ordered lists of instructions are called programs, and they consist of a few basic types of instructions, as we said in our example before. So you need to load data from the RAM to registers, and you need to perform arithmetic operations in the ALU, and again you will need an instruction to store the data from the register to the RAM as a result of calculation. The DLW1's basic architecture and arithmetic instruction format. The LW1 is a microprocessor, and it is a very simple microprocessor that contains from three main parts: ALU, main memory, and four registers named A, B, C, and D. The DLW1 is attached to a bank of main memory that's laid out as a line of 256 memory cells numbered from hash 0 to hash 255. The simple hash means address. Without hash, it means data. The DLW wants arithmetic instruction format. Of course, if you need to perform an arithmetic operation, you have to tell the microprocessor what to do. You can do this using the instruction format. For example, if you are talking about arithmetic operation, you need to include in your instruction format at least the instruction type, means add or subtract, the two sources of data that you will use for addition or for subtraction, and of course you have to show your destination to store the result of your arithmetic operations. So they are the minimum required information in the instruction format for performing an arithmetic operations, and it will be used by the microprocessor. We have here clear example using assembly language. We have codes and we have comments. In this case, the comments help us to understand the meaning of the code. For example, the first line we have load hash 12A. This means that our data, or the first number, is loaded from the RAM or the main memory from the address hash 12 into register A. The second line, the same as line number 1, but in this case we are reading data from another address into register B. The third line is to perform the addition operation, add the contents of A with the contents of B, and store the results in register C. Finally, you have to store the final result, or to move the final result from register C back to the RAM to the address hash 14. So now your program to add two numbers is performed using 4 lines as minimum. And here we have the change. What is the changes made in the RAM before and after running our addition program? As you see in the address 12, I have the data 12, the address 11 I have data 12, the address 12 I have data 6, and the address 13 I have data 2, and the address 14 I have data 3. After running the program, what are the changes? As you see, I didn't use the address 11, there is no changes, and I didn't overwrite the addresses 12 and 13, but I used the data for addition, and I stored my result to the address 14. So as you see, the data before running our program, it was 3, and now it becomes 8, which is the result of summing 6 plus 2. Memory access register versus immediate. Now, real computers have billions of possible locations in which data can be stored. So, programmers need a more flexible way to access memory, a way that doesn't require each memory access to specify numerically an exact memory address. So, modern computers allow the contents of a register to be used as a memory address, a move that provides the programmer with the desired flexibility. We said before, we used registers for two things: as sources of data and as a destination. In this case, or now, we are using registers, the data stored in registers, as an address to access the main memory or RAM. Register as a memory address. We have now an example. The first line, load hash DA. Hash means address. As you see here, we used the data stored in the register D as an address to access the main memory. If the data stored in register D is 12, we will use this 12 as an address to access the main memory and load the data from address 12 from the main memory to register A. The other steps, they are known by you, and finally we will store the result to address number 14. So the only difference between this example and previous example, in the previous example we immediately accessed the memory to load the data to registers, but now we used the data stored in D to access the RAM and loading the data to register A. In this case, we are using the address number 11 to load data to D, and after that we are using the data stored in D as an address to access the memory and load the data to be stored in register A. So the difference between this program and the previous program, that we prepared the data in register D before using this data as address to access RAM or memory again. Register relative addressing. This is the third type of accessing the main memory or RAM. In real-world programs, loads and stores most often use register relative addressing, which is a way of specifying memory addresses relative to a register that contains a fixed base address. And it is very simple. You are using the address in one of the you are using the data in one of registers to access a specific address in the main memory. Well, this we call base address. After that, you have to move several bytes that we call offset to go to your desired address, which means now your data is stored as sequence byte by byte, but what only you have to know is only the first or the base address. After that you can go several bytes to the desired address. So we have a data segment is a block of contiguous memory cells that a program stores all of its data. An offset is the distance in bytes of the desired memory location from the data segment's base address. We have an example here of register relative addressing. The code load hash. As we see, D is we are using the data in D as base address. Plus 108, it is the offset. This means for us, I will use the data in the register D to access the main memory and from as a base address, and from this location in the RAM, I will move 108 bytes until I will reach the desired address. And it is the same for storing. So we can use register as for loading and for storing the results. I have to mention one thing, that the registers in the DLW1 microprocessors A, B, C, and D we call general purpose registers. We can use these registers as the data to be used by ALU, or we can use data in registers for addressing to access to the RAM, or we can use these registers to store the result of arithmetic operations as the output from the ALU. So because we can use these registers for loading, for storing, and for addressing, we call these registers general purpose registers. So we can see now we have three main methods to access the RAM. We can access the RAM directly using direct address, or we can access the RAM using data stored in one of the registers, or we can access the memory using the data in one of the registers as a base address, and after that moving an offset byte data that we call register relative addressing. Thank you very much for your listening. You can refer to the textbook inside the machine 207. See you in the next lecture or lesson, and I hope you all success.